much. It's like you're formalizing a lot of stuff about basic computability in order to even get to the interesting bit. So McAllister pointed out that you could adapt ideas from the infinity models. That rings a bell for anyone. Anyway, so that led to this sort of step index logical relation idea. The initial paper was just recursive types. My thesis extended it to type safety for references, recursive types, and polymorphism. This paper did what I showed you yesterday. I was pointing you to an ESOP 06 tech report. So that's what this was. And then in 2009, with Derek Dreyer and Andreas Rosberg, we had this, and by the way, I stopped at 2009. We did a logical relation which you could use to prove equivalence of lots of really sophisticated and interesting examples in the presence of state and polymorphism. Okay, I'm not going to go through any of this. Let's see how much I have time for. I've already said stuff about foundational proof carrying code. So this slide has a bunch of instances of unary step index logical relations. All right, so using them to prove type safety. FPCC did this for all the things that I just mentioned, and the main thing here was that we built a model of a low-level typed assembly language, all right, which was the target language of a compiler for Core ML. And then if you're interested in substructural types, linear types, and so on, you can look at some of these references, work that Matthew Fluid and Greg Morissette and I did on doing type safety in the presence of, when you have linearity and affine types and so on. And for those of you interested in objects, Jan Schwinghammer and Kaplan, is that how you pronounce it? Catalin have this paper where they do type safety for Abadi-Cardell's imperative object calculus, which is very nice, and it sort of gives a more relaxed sort of formulation of some of the things from my thesis in an object setting. I was telling someone about this yesterday. Okay. Andrew Appel and Aquinas Habor and Francesco Zappernardelli have used this in the setting of CompCert. So they they proved the soundness of a concurrent separation logic with respect to this concurrent C minor operational semantics. And the whole point of this was to come up with the semantics to adapt Xavier's CompCert proofs to a concurrent setting. Let's switch to binary logical relations. So I've already talked about some of this. A very nice paper. So I mentioned this Popple 09 paper with Derek Dreyer and Andreas Rosberg, which was the first to do this, state plus type abstraction kind of thing. But there's a follow-up paper. Derek Dreyer and Lars Birkedal and Georg Neis, as far as higher order state is concerned, or mutable references that can store functions, etc., are concerned, this paper isn't more powerful, but it's more elegant. So they took all of the initial ideas that we had in that Popple 09 paper and made it sort of more beautiful. And they have this notion of state transition systems. So the worlds, I said to you that the worlds need to be more complicated to express interesting relations between the states of your two programs. And these state transition systems allow you to sort of write down a protocol that you expect to hold in the, as you go into the future, as you run your program at a high level. Okay, I'm not going to talk about this. One thing I should mention. There was a paper that, how do I say this? I have used step index logical relations in a setting where there were no types. And that's a very important thing to be aware of. If you want a reference, it's this Popple 08 paper of mine. But never mind that, it doesn't matter. The important bit here is that once you start to do, once your induction is defined using steps, right, using the K, you don't really need to do induction on types anymore. Until then, or until step index logical relations, you couldn't, everyone always said, but logical relations can only be used in a typed language. This was a comment that was pervasive. And it's not true anymore, and it's good to be aware of that. So if you need to use this sort of technique to break circularities, just do induction on the steps and forget about types. You don't need them. I'm going to talk about this work. Yes, compiler correctness, since Xavier is talking about compiler correctness. So I've said that you can, okay, let me start out with an observation. Maybe Xavier has pointed it out already. In CompCert, the compiler, the theorem that you prove, that compilation is semantics preserving, applies only to whole programs. Okay, so if you compile, you know, a program component, a module, something, down to assembly, and then you link it with some library code, maybe some runtime libraries or something else, or maybe you wrote some components in another language and compiled them down to assembly. You want to link with those. At that point, if you're linking with code that was not compiled by CompCert, then you don't have any guarantees of compiler correctness, formally speaking. Okay, and I think this is a fascinating open problem, a really, really important one. Nick Benton has put forward a really, you know, has put forward one way of doing compiler correctness for so-called open programs, programs that are not whole programs. He calls it compositional compiler correctness. I don't like the term so much, so I just wrote open programs. And the idea, as I've been saying, is to set up a logical relation between source and target. This logical relation acts as the specification of the relationship that you want between, you know, high-level code and low-level code. When does a piece of low-level code correctly realize a piece of high-level code? Benton and Her have done this for, you know, have done this for System F down to an SECD machine. So they've shown compiler correctness. And Her and Dreyer have extended that to, you know, to a source language with mutable references. But what they do is they set up this logical relation between source and target. The technique doesn't work right now in the context of multi-pass compilers. You have to set up one logical relation between the absolute source and the absolute target. So you can't implement your compiler the way we normally implement compilers in multiple passes. Okay? And this has to do with this weakness sort of they're using step index logical relations. This has to do with proving transitivity. You know, you have one logical relation set up that relates source language to intermediate language I, and another one that relates intermediate language I to target language T. And now you need to say that now that you've proved these two things, right, your first compiler pass and your second compiler pass are correct, you want to conclude that your full compiler is correct. Don't have that property. Okay? Now, that's one problem. The other problem is more subtle. So here's the theorem that you actually prove. You prove that if you have a source language, a source program little s of type big S, and it compiles to some target T, then the theorem that you're proving is that S is related to T. And the big S that we put over there is the type of the source, not the target. But anyway. Now, the consequence of this, the reason this can handle open programs, is this bullet here. If you have, so let's take a look at what happens with the function rule, right? If you have a source program that's a function, S prime to S, and you are given an S prime, then if you know that S is related to T, and S prime is related to T prime, then just by the definition of logical relations and how they're set up, you immediately have that S prime applied to S applied to S prime is related to T applied to T prime. This is the notion of composition. This is how you can take an arbitrary T prime and hook it up with your T. So you compiled S to T using CompCert or, you know, your certified compiler, and now you are given a T prime. So notice if I use my verified compiler to compile S to T, if I now want to link with T prime, what do I need to do? Based on the bullet that I put up here. If I want to reason about linking with T prime, I need to write down an S prime that is related to that T prime first, right? This is not good, right? Because someone could give me some piece of target code to link with that's like a few hundred lines of assembly, and I wouldn't be able to decompile it to figure out an S prime, right? So this is, I think there's still, you know, a lot of work to be done here. Does that make sense to people? Do people want to talk about it? Okay, I'm really interested in this problem right now. So, okay, Benjamin has used binary step index logical relations in the context of differential privacy. There's a very nice ICFP10 paper, and I think this is still ongoing work that Marco is doing with Benjamin. And most recently, we have just written a paper about a logical relation that you can use for reasoning about equivalence of fine-grained concurrent data structures. And we can handle many, many sophisticated examples, so it's kind of cool. It's very complicated, though. OK, I am not going to go into various things. There's been a lot of work on hiding the steps. OK, you can do this in two ways. I'll mention this one. You can sort of build a relational logic on top of the step index logical relation and essentially hide all the steps, except in a few places you'll have this later modality. And those places will mark where you need to go down a step. That way you don't have to, you can use the logic to prove equivalence of programs and not have to worry about the, turning the crank with the logical relation itself. So this makes the proof method easier to use. This work in direction theory makes these logical relations easier to mechanize. Okay? So if you're interested in mechanizing this stuff in Coq, go look this up. Hobart, Dawkins, and Appel, Popple 10. I should stop. Let's see. Okay. Yeah, let's stop there. You guys can look at the slides, and there are references there, and if you find some of them interesting, just pull them up. Okay, thanks a lot.